If my thing would unfreeze. There it is. All right, so if we look at the very first one, remember some of these things can be shown from the equation, whereas some of them you actually have to put into Desmos. So the first one is one of those where you kind of have to use the equation. So it says an object is 4,900 feet above the ground. The object falls, and its height is given by a quadratic function. There's that function. The height of the object above the ground is in feet, and time t is in seconds. So the first question asks, what is the object's initial velocity? So that comes from the equation. So we talked about this yesterday. Which value of the quadratic equation tells you velocity? The b value. Now here's the question. Do I have a b value? No. So what's the velocity? 0. 0 feet per second. Which makes sense because it says that the object falls. So there wasn't any other force that caused the ball to be launched into the air. It's more like someone just dropped it out of their hand. All right, they just opened their hand up, let it drop, let gravity do the work. All right. Now, what is the object's height after 10 seconds? So what would you put into Desmos to get that? X equals 10, and what are you finding? Where it intersects. So what'd you get? It's what? 3,300 feet. Then it asks, how long is the object in the air? So this is a key feature. Which key feature would tell you how long it's in the air for? The x-intercept, specifically which one? The positive x-intercept. So what was your answer? 17.5 seconds. Good. Now, remember what I also said. Sometimes, all right, so remember what I also said. Sometimes they don't flat out give you the function, but they give you enough information to write it. All right, so this next one is an example of that. So a model rocket is launched from the top of a cliff, 384 feet high, with an upward speed of 160 feet per second and the gravitational pull of 16 feet per second. So, since it's in feet, we're automatically going to put our negative 16x squared. You're always going to start with that. So, when it comes to these, depending on whether it's in feet or meters, you always are going to start with either negative 16 or negative 4.9. All right, so 16 is feet, 4.9 is meters. What comes next? Plus 160x, because that's my velocity. Then what? Plus 384, because that's my initial height. So that would be what you would end up putting into Desmos. So now it asks, after how many seconds after the launch does the rocket reach its maximum height? So first off, maximum height. What key feature gives us that? The vertex. Now, since it's asking for how long it takes to get there, what value of the vertex are we using? The x value. So what'd you guys get? 5 seconds. Now the next question asks what actually is the maximum height. So we're using the vertex still, but now we're using what? The y. So how many feet is that actually the maximum height? Say that one more time. 784 feet. All right. Now, it then asks, how many seconds after the launch does the rocket reach the ground? So reaching the ground, that's which key feature? Positive x-intercept. So what'd you get? 12 seconds. Any questions on 1 or 2? Now, 3 is not necessarily a projectile motion, but the logic that goes with how you determine which key feature to use for projectile motion still applies with 3. All right, so it's kind of pretty much the same process. You just have to think about it logically. So 3 says, in order for Mr. Moore to decide how much fertilizer to apply to his corn crop this year, he reviews previous records from previous years. So his crop yield Y depends on the amount of fertilizer he applies to his fields X, according to this equation. And it wants to know what the highest yield possible is. So here's my question. Highest yield possible. There's a key feature that you would use for this. Which one do you think it would be? The Y value of the vertex. Good. Because it's talking about yield, which they said yield is Y. And it's talking highest, so we can take that as max. So that would mean vertex. So what ended up being the Y value of that vertex? 16? So I would say, because I don't really know the units here, so the crop yield of 16, whatever that means. All right, last one. So don't be fooled. It's still projectile motion. It's just in meters instead of feet. So it asks, how high is the ball after 1 second? So what would I do? First off, x equal to 1. All right, so how high is the ball after 1 second? It's what? 20.6 meters. Good. Then it says, find the maximum height of the ball to 1 decimal place. So we know that's vertex, specifically of the Y variety. So what is my maximum height? 31.6 meters. It then asks, when does the ball reach its maximum height? So again, still vertex, but now it's the X value. So how long did it take to reach that height? 2.5 seconds. And then finally, when does the ball hit the ground? So that's clearly the positive x-intercept. So that would be what? Say it one more time. 5 seconds. Okay. So overall, projectile motion is really easy. The hardest part is just figuring out which key feature to use. And then which value of said key feature to use. All right, so that's really the only thing you gotta be careful about. And again, usually the little blurb that they give you at the start of the question tells you what X and Y means. But if it's projectile motion, typically height is always the Y value, time is always the X value. More often than not, time is almost always X in any scenario. All right, any questions on that? So today we are going to learn a brand new form of function called the vertex form of a quadratic. So we talked about standard, now we're talking about a different form, which is vertex. Still gives us the same quadratic graph, it's just written differently. So go ahead and completely close your Chromebooks. We don't need them anymore, but you may want a calculator if you have not already grabbed one. Or Ayla, just put your name on the board. I got someone out. All right, so vertex form of a quadratic. So we know that the standard form of a quadratic is what? How we typically write out the standard form of a quadratic? Good, ax squared plus bx plus c. Now, a quadratic can also be written in what we call its vertex form, which we'll go over in more detail, but it's essentially a times x minus h squared plus k. That's typically the formula. Now, I'm not going to tell you specifically what it means yet, but basically when it comes to forms of quadratics, a lot of times those forms give you specific key features right off the bat just by looking at them. So for example, standard form, we can look at it and tell what the y-intercept is because of the c value. Vertex form, what do you think it's going to tell us? It's probably going to tell us the vertex. It's in the name. All right. So before we get to vertex form, let's actually look at the parent function. So we talked about this before earlier on in the units. But remember, the parent function for any quadratic is x squared. So remember, parent function just means that every quadratic function in existence comes from x squared. It's a transformation of x squared. All right. That's why it's called the parent function. It's where it all began. All right. So first off, if I just state some x values, so I'm just going to state, like, if you put it into Desmos, what you would typically get. All right. Now, so without using a calculator, because this is a really easy calculation, what's the only thing I'm going to have to do with those x values to get my y values? You just got to square them. So what's negative 2 squared? Negative 1 squared? 0 squared? 1 squared? 2 squared. Good. Now, can anyone, without graphing it yet, identify the vertex? Because it's on this graph. It's 0, 0. Why do you think it's 0, 0? Because it's what? It doesn't repeat, and it's also kind of the spot where all the other y's start repeating. All right. So I'm going to take a minute, do a quick graph of this, because we already got the table. So 0, 0 is my vertex. I got 1, and negative 1, 1's its buddy. 2, 4, negative 2, 4 is its buddy. And just for funsies, let's actually extend this a little bit. If I picked x equals 3, what would the y value be? 9. So 3, 9. So its buddy would be at negative 3. So this is what my graph would look like. Now, because 3 squared is 9. Now, we can actually graph a quadratic without using a table. All right. So there's actually a pattern that happens with quadratic functions. And the way it works is that just like, because you know how with a slope intercept form you can do rise over run? Kind of like that, but slightly different. Takes a little bit more thinking. So it's more like run over rise. So if we run x units from the vertex, we would rise ax squared from the vertex. So what that means is that if we go over x units from the vertex, so for example, let's say I went over the 3 units. So from the vertex, I went over 1, 2, 3 units. Now, my a value in this case is 1 because there's nothing in front of it. The coefficient for a is 1. Crap. I hate when it does that. So all I got to do is take that 3 and square it. So what's 3 squared? So I take my run and I square it. That's what? 9. So then my rise is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, while that looks like, well, didn't we already do that when we made the table? Yes, but that's because it's the parent function. You'll see it more when the vertex is shifted away from the origin. All right. So just something to think about. We'll practice it more with non-0, 0 vertex. All right. Any questions on the parent function? Now, let's look at this next function. So in your TI, what I want you guys to do is, as I showed you how to do this the other day, I want you to graph that in your calculator and look at the table. All right, because then from the table, you should be able to identify the vertex, the axis of symmetry, whether it's the max or min, the minimum value, and the y-intercept. So just for help with that, all right, everyone look up here. You're going to hit y equals, clear the equation if it comes in. Also, for whatever reason, if your plot, if it's plot 1 up here, if it's highlighted, just use the up arrow key so it's flickering over it, hit enter so it's unhighlighted, because if it's highlighted, it won't graph. All right. Now, I'm going to type in exactly as I see it. So I'm going to type in parenthesis x plus 4, square that, and then plus, nope, minus 5. And then who remembers how you make the table again? Second graph. So look through the table, use the up and down arrow keys, and see if you can figure out where the vertex is, where the x-intercept is. Not the x-intercept, the y-intercept, where that is, and the axis of symmetry. And if you don't like the table, you could have also used the calculation function on the TI if you want to, but I think the table's a little bit easier. Yes, sir. It's okay if it goes off the graph. We just want to know what the y-intercept is. We may not actually graph it. So, what is the vertex? So if I look at my calculator, if I'm looking at the table, which point here do you think is my actual vertex? It's what? -4, -5. What kind of clues you in for it being -4, -5? It doesn't repeat, but also, if you look on either side of it, you see a -4 and a -4. That's kind of a good clue in that that's the vertex. All right. So it would be -4, -5. Now, just for funsies, just to double check, instead of using the table, I'm also going to use the calculation feature. So I'm going to hit graph first. Then remember, you're going to hit second and then trace. And is that vertex going to be a max or a min? Was that vertex a max or min? It's a min. So I'm going to hit 3 to calculate that minimum. All right. Then you use your arrow keys to go left bound. Axis symmetry. If you have the vertex, you have the axis symmetry. Yeah. It's the x value of the vertex. So if I go left bound, I'm going to go slightly to the left of the vertex, hit enter. Right bound, I'm going to go slightly to the right of the vertex, hit enter. My guess, I'm going to try and get right on top of the vertex if I can. Doesn't have to be perfect. All right, that's pretty close. Hit enter. It says it's -3.99, which can round up to 4. Typically, if it does that, you usually round it up anyway, and then -5. So we were right. Now, axis of symmetry is just the x value of the vertex, so how would I write it? X equals -5. Not -5, -4. We already said that it was a min. Who remembers what I told you guys minimum maximum value means? It's the y value of the vertex. So the y value of my vertex is -5. What'd you find the y-intercept to be? It's what? Not just 11. One has point 0, 11. How'd you know that was the y-intercept? Because in the table, the x value would have been 0. All right. Now, we're not going to worry about transformations just yet. We're first going to graph this. All right. So I have -4, -5. Now, I know that you have the table pulled up in front of you. All right. So that's a good way you can get points. Just make sure you're going on either side of the vertex. But I want to show you the pattern first. Okay. So based off of the function and where my a value is, the a value is positive, so I know it's going to open up. All right. Then if I run x units, I will rise. If a is 1, that means it's 1x squared. So what that means is if I go 1 unit away from the vertex, what's 1 squared? 1. So that means I'm going to rise 1 point from there. Now, the great thing is that since we know the axis of symmetry is right here at -4, we can find its reflection buddy on the other side. Now, let's say I go 2 out from the vertex. So my run is 2 out from the vertex. So that means my rise will be what? 4. So I'm going to go up 1, 2, 3, 4. And then on the other side, find its reflection buddy. One more. If I go out 3, what would be my rise? 9. So I would go up 4, 5, 6, 7, 8, 9. And then find its reflection buddy on the other side. So if I graphed it, it would look something like this. Now, if I list out all the points that I just had, all right, I'm going to keep the vertex in the middle. If I list out all those points that I just graphed, I had -7, 4, -6, -1. Put this a little lower. -5, -4, -4, -5. Then -3, -4, -2, -1, and -1, 4. Is it true that that table matches the table that's on your calculator? Yes. All right. So even if you didn't have that table, you could still found that. So again, to each their own on what you like to do. If you want to put it in the calculator, generate a table, that's fine. If you want to use the pattern, that's fine too. I don't care which way you do it. Now, here's the question, transformation-wise. So think way back to Unit 1. Remember, every quadratic is just a transformation of x squared, which is its parent function. So I like to base it based off of the vertex. So first off, just like take a gander at the two graphs. I know it's small on the board, but look at your page. You can't see it. What does it look like happened? Like, I don't want specifics, but what type of transformations do you think happened? Charlie. So I think it shifted some. Now, remember, it's not drawn to scale, so it may look like it was a dilation, but in reality it didn't because we don't have an A value. That's not 1. All right. But I do agree that it was a translation. Now, to find that translation, I always just like to look at it through the vertex. All right, so the vertex of the parent function, my pen would work. Oh my God, I hate this thing. So my vertex is right here at 0, 0 for my parent function. So that's my parent function vertex. How do I get from my parent vertex to my new vertex? What do? Left 4 and then down 5. So let's say I wrote an arrow notation. So XY. What did I have to do to X or 0, 0 to get to -4? You subtract 4. What do I have to do to the Y? Subtract 5. So take a minute. Do you guys see any connection between the original function and what we just wrote out in arrow notation, the transformations? Yeah, what do you see? So we have a -5 here, right? But this +4, where do you think that comes from? I gave you the function. So I actually gave you the formula already for vertex form. Do you guys notice how a minus is in the formula? Well, what happens when you multiply a negative by a negative? Positive. That's why. So this right here, the signs just flips. This is actually x minus -4 squared. So in other words, did vertex form actually give us our vertex? Yeah, it did. So that's what we're kind of going into next. So vertex form. It's very easy. It's always y equals a times x minus h squared plus k. Where the a value still determines the direction of opening and the pattern multiplier. So in other words, let's say the a value was 2. That means if you ran x units from the vertex, you would rise 2x squared, which you'll see one like that in a minute. The axis of symmetry will be x equals h. The vertex would be hk. And for the y-intercept, we don't have a nice pretty place you can see the y-intercept like in standard form, but you could substitute 0 in for x and solve for y. Or just look at the table. Now, something to note when it comes to signs. So when you're pulling out, when you pull out that h from the equation, you flip the sign. Whereas the k, you keep the sign. So remember, x minus h is its natural form. So let's say it was x minus 1. That means the x value of the vertex is 1. But if it was x plus 1, it would be -1. All right? So just remember to flip the sign when you go between the function and the vertex. But k, you just always keep it. So let's take a looky-loo at here. So look at this next vertex form. What's the a value? -1. So since we have a negative right here, and there's nothing else in front of it, we say it's -1. So the pattern would be if we run x units, we would rise ax squared, so -x squared. Now, I want you guys to think about this logically. Since our a value is negative, what does that say about our graph? It's going to what? It'll have a maximum. Which way will it open? It'll open down. So I want you to think about this logically. Let's take an idea of what's going to happen. All right. So between the parent function and this new function, what transformations do you think are going to happen? So for starters, since we know it's going to open down, what direction does the parent function open? It opens up. How do you think we go from opening up to opening down? Reflection over what? The x-axis. Good. So what's going to happen is we're going to reflect over the x. All right. That's how we get the minimum to become a maximum. Now, we know there's going to be a shift because the vertex is going to be different than 0, 0. So the way to find it is to actually figure out what the vertex is first. That's probably the easiest way to see it. So what actually is the vertex? So if we look at the function, what's the vertex? It's what? So what's the vertex? What's the h value? It's 1. Because remember, since it's -1, we flip the sign. That's our h value. And then what's the y? What's my k value? 3. So that's my k value. So my vertex is 1, 3. So now think about that in relation to the parent function's vertex 0, 0. What kind of translation do you think will happen? So if I'm at 0, 0, horizontally, I want to go 1 unit, positive 1 unit. So would I go to the left one or the right one? Right. So we would go right 1, and then what? Up 3. Good. So yeah, guys, the whole reason we did geometric transformations is because function transformations are also a thing. It's actually a big part of Math 3. All right. So that's why we did the geometric version of it first, because it's easier to understand and then apply it to functions. All right. So let's do some graphing here. We'll get the y-intercept in a minute. But, so I'm going to start with my vertex. So that'll be 1, 3. So right here. Now, I'm going to use my pattern for this. But again, if you don't like the pattern, you can always plug that whole function into your calculator and generate a table and use some happy points. All right. So for the pattern, if I go out 1, all right, what's 1 squared? What's 1 squared? 1. And then if I make it negative, -1. So that means I'm going to go down 1. And then since my axis of symmetry would definitely be right here, I'm going to find its reflection buddy. All right, now let's say I go out 2. What's 2 squared? 4. So times a negative, that's what? -4. So I'm going to go down 4 units. So 1, 2, 3, 4. So right here. And then using the axis of symmetry, find its reflection buddy. So right there. Oop, too far. The reflection buddy's right there. All right, what if I go out 3? So it'd be +9 or -9? -9. So we'll go down. Here's 4, 5, 6, 7, 8, 9 units. Then use the axis of symmetry to find the reflection buddy. And we can probably stop there. So my graph will look something like this. So typically when I ask you to graph a quadratic, I want at least 5 points, including the vertex. All right, we actually graph 7, but you know, sometimes I just like to get as much as I can fit on the graph, so I get a good idea of what the picture looks like. Now, if I write out all my points, all right, I have -2, -6, -1, -1, 0, 1, 1, 3, 2, 1, 3, -1, 4, -6. So if I graphed, or if I put this function in my TI and generated the table, would I get the exact same table? Did you check it? Yes, you would. So what's the y-intercept? So it's on the graph already. What's the y-intercept? Oh, I'm sorry. I put 1 instead of 2. That should be a 2. My apologies. It's Friday. It's the end of the day. That should be 2. My bad. So yes, it's 0, 2. That's probably what was throwing y'all. Now, just to double check, if we did this by hand, I could also find the y-intercept by replacing this x up here in my original function with 0. Because remember, for y-intercept, x is always 0. So if I do negative 0 minus 1 squared plus 3. What's 0 minus 1? What's negative 1 squared? Times a negative. So I got negative 1 plus 3. Is that not 2? Yeah. All right, one more. And then we'll move on to a different thing. So, first off, what's my a value? Negative 1/2. So that means my pattern would be if I run x, I will rise negative 1/2 x squared. What's my vertex? 2, 5. Good. So my axis of symmetry would be x equals 2. What transformations will definitely happen? So think about from the parent function. What's definitely going to happen? Not rotation. Translation. What's the translation, do you think? Right 2, up 5. And again, the way you can think about that is if you look at the new vertex, compare it to 0, 0, think about what you have to add or subtract to 0 to get to that new vertex. What else is going to happen? What directions is this going to open? Down, because it's negative. So that means we have to also do what, transformation-wise? Reflect over what? X-axis. Now, there's one more transformation that's going to happen. What do you think it's going to be? A dilation. What do you think the scale factor is? Not a negative half, just a positive half. All right. So it's a dilation by a half because remember the negative sign, that's what tells us we have a reflection. All right. So I'm going to say it's going to dilate by a half. All right. So I want you guys to take a minute, see if you can graph that on your own. So again, you can use the table in your calculator or you can use the pattern. I'd like to see if you can do the pattern. But you can always check using the table in your calculator. So everyone should be, take a moment, graphing that back. So my suggestion when you do the pattern, when you do your run, use even numbers. So like instead of going over 1, go over 2. Because you're going to end up multiplying by a half, which is the same as divided by 2. Even still, odd numbers squared are odd numbers. But you have to square first. So 2 squared is. You can always check the table on your calculator so you have it ready. All right, guys, let's see what you got. So I'm going to use the pattern, just so if you want to use the pattern, you can see it. But again, if you generate a table and plot points that way, that's fine too. So my vertex is at 2, 5. That has to be plotted first. Now, because we're ending up having to multiply by 1/2, meaning we're going to divide by 2, I'm going to use, my run is going to be even numbers. Because you may not know this, but whenever you square an even number, it's always going to be even. But whenever you square an odd number, it's always going to be odd. I don't want to deal with fractions. All right. So I'm going to go out 2. All right. So what's 2 squared? Times negative 1/2? Negative 2. So I'm going to go down 1, 2. Then since the axis of symmetry would be right here, I want to find its reflection buddy, which would be over here. Then I'm going to go out 4. So 1, 2, 3, 4. All right. What's 4 squared? 16 times negative 1/2? Negative 8. So I'm going to go down 2, 4, 6, 8. So right here. And then I'm going to find its reflection buddy on the other side. Now, it says at least 5 points. That's 5 points. So I have enough. Plus, I think if we did any more, it would go off the graph. Now, again, if you're more of a put it in the table type person, my suggestion is pick happy points. So what I mean by that, I wouldn't use decimals, all right? Even though it would just give you halves, and halves are pretty easy. That's not always the case. Plus, you want it to be as accurate as possible. All right. So my suggestion, pick what I call happy points, which is just, silly talk for whole numbers. All right. So whole number y values. All right. So that's enough of the key features, like using the equation to graph. Now let's do the opposite. So look at example 5 on the next page. So example 5. Now we're going to write the vertex form equation given the vertex and a point. All right, so just so you have it for reference, vertex form once again is y equals a times x minus h plus k, where hk is the vertex. All right, so yes, sir. Yeah, it would help if I put the little square there. That's what makes it quadratic in the first place. I do that crap all the time. All right. So our vertex is 4, 3. So we're going to start out with y equals a, because we don't know what our a value is yet. X. All right. What's my h value going to be? 4. So would I put minus 4 or plus 4? Minus 4. Squared. Because remember, with the h value, you end up having to flip the sign because the minus is in the formula. All right. Then, what's my k value? 3. So it'd be plus 3 or minus 3? Plus 3. That's the sign that you keep. Now, I'm not done because I still got to find my a value. How do you think I can use the other point that they gave me to find my a value? Right, just plug them in for x and y. So x, plug it in for both of these, solve for a. So if I do that, I got 5 is equal to a times 5 minus 4 squared plus 3. So what's 5 minus 4? What's 1 squared? 1. What's 1 times a? A. So this would be 5 is equal to a plus 3. How do I solve for A? Subtract 3. So 2 is equal to A. So do not assume the A value is 1. All right, sometimes it's not. All right, so you have to always solve for A if that's always the case. So my final answer would be y is equal to 2 times x minus 4 squared plus 3. Since they asked for vertex form, we can leave it like that. Now, in a little bit, we're going to convert from vertex form to standard form. So you can convert to all the different forms. So the 3 forms are standard form, vertex form, factored form. All right, factor form we won't really see till 3.7, and even then we'll mostly see that in unit 4. All right, but vertex form and standard form, what's going to happen is on Monday, we're going to talk about how to convert from standard form to vertex form, which will require a new skill called completing the square. So we're going to learn all about that on Monday. All right, but just for now, let's try another version. All right, so let's look at example 6. So it's still the same premise, but instead of them flat out giving us the vertex and a point, we have to pull them from a graph. All right, so what is my vertex on this graph? 0, 2. Now, I want one happy point, meaning it lines up perfectly with 2 whole numbers on the graph. All right? It's, did you guys say 2, 0? Yeah, 1, 0. That works. Right, so you could have used 1, 0 or you could have used negative 1, 0. Doesn't matter. All right, I just need one happy point. So I'm going to use 1, 0 just so I don't have to deal with negatives. All right. So we're going to start by putting in the general vertex form. So y is equal to a times what will go in the parentheses? X minus 0 squared plus 2. Now, we know that x minus 0 is just x, but for right now, we're just going to leave it alone. Okay, I'll show you how to simplify it in a minute. But now we're going to use our pretty point, 1, 0, to solve for a. So I'm going to do 0 is equal to a times 1 minus 0 squared plus 2. What's 1 minus 0? Squared. 1. A times 1? A. So a plus 2 is equal to 0. How do I solve for a? Subtract the 2. So negative 2 is equal to a. Does that make sense for negative 2 to be the a value? Well, think about it. What direction is the graph opening in? Down. So that means the a value has to be what? Negative. So that makes sense for us to get a negative value for that answer. So if I rewrite this, I get y is equal to, not a, negative 2 times x minus 0 squared plus 2. Now, if you want to simplify this down further, because more often than not, like if you see it on a test or something, they would. All right. What's x minus 0? X, and then you just leave it as x squared. So the other way I would take it is negative 2 times x squared plus 2. So this is one of those rare instances where not only is it in vertex form, when you simplify it, because 0 is one of those values, the vertex form can also double as its standard form. All right. It doesn't always happen, but it does happen occasionally, mainly when your x value of your vertex is 0. That's when it happens. Because if you think about it, this version does look like standard form to us, just doesn't have a b value. Any questions on how you get the equation from the graph or from the vertex and a point? All right, last thing we're going to do. So last thing we're going to do today is take vertex form and convert it to standard form. So it actually requires skills that you already know how to do. It's actually not too bad. Because, first off, if I look at letter A, we know we're going to multiply by -1 at some point. But remember, due to PEMDAS, we always handle what first before multiplication? Exponents. How can I rewrite x plus 3 squared? Nope. Well, yeah, you're jumping ahead of the curve. But if I just wanted to rewrite x plus 3 times x plus 3. So what Riley was doing is that they were already going ahead and jumping into after they do the box method. All right. So, which, if you know that's a perfect square trinomial, that's easy to do. All right. But if you don't know how to get a perfect square trinomial, you can always just do a simple box method or FOIL, whatever. All right. So this will be x squared, 3x, and 9. So I have a negative times x squared plus 6x plus 9. Which, Riley, was that what you were going for? Were you going for x squared plus 6x plus 9? Yeah. So, for me, since I've done this enough, I can jump right to the trinomial without doing a box method. But that's just because I know what the rule for perfect square trinomials are. All right, which really all it is you square the first term, square the last term, and then the middle term is twice whatever the two terms multiplied together are. So 3 times x is 3x, times that by 2, 6x. Now, what's my last step to get this in standard form? Distribute that negative. So this would be y is equal to negative x squared minus 6x minus 9. These two functions are the exact same function. If you graphed both of those in Desmos or your graphing calculator, they would generate the exact same graph. The only difference is that the first one's in vertex form, the second one's in standard form. Just because they're different forms doesn't mean that they're not the same function. All right, last one we're going to do. So what will be my first step to converting this? Multiply x minus 1 times x minus 1. So just for time's sake, I'm not going to do the box, but just know you can. So I have x squared, -1 times x is negative x, times 2, that's negative 2x. -1 times -1 is positive 1. So that's what I get when I do this calculation. Now, since I got stuff outside of it, I'm going to put that in parentheses and bring down the 2 and the plus 5. What do I need to do next? Distribute. Did I really say distribute? Distribute that 2. This would be 2x squared minus 4x plus 2. And again, bring down that plus 5. Don't forget about that little stinker. What's the last thing I do? Add the two like terms together. So 2x squared minus 4x plus 7 is equal to y. There's my standard form. Again, if you graphed these two functions, it would literally be the exact same graph. They're just in different forms. All right, so your homework for tonight or over the weekend, you're welcome. It's not a Delta Math. It's pages 27 and 28. I'll check in on Monday. Now, don't forget that Delta Math that I assigned yesterday. I believe that is due tonight, though. So make sure you knock that out if you haven't done so already. So, guys, just so you're aware, I'm thinking test next Thursday. All right. So next Thursday, that's why I'm thinking test. So I'm telling you guys this just so you guys can get an idea of how you want a timeline doing your journal.
I don't think I'll be here.
That's okay.
I'll be here for 5 minutes.